Hello everyone and welcome to section 3.1 of statistics. In this section we talk about measures of center, the mean, median, the mode, and a couple other ones. So let's get started. Measures of central tendency or measures of center. So suppose we want one number. To describe the central or typical value. So we're looking for one number that is like a typical value in an entire sample or population. Such a number is called an average. There are many ways to compute averages. We will consider a few of them in this section. So there are over a dozen ways to compute an average, and in each case you could say the average is and state a number. So if you remember from the first day of class, this word average, you have to be careful about this word. You really need to get more detail. If somebody tells you the average number is blank, you're going to really, if you really want to understand, you're probably going to have to ask for more detail about how the average was calculated, what kind of average, and things like that. So we looked at an earlier example where we had the annual wages and thousands of employees at S-Mart. And we looked at this one from the first day of class. And we talked a little bit about mean, median, and mode. And we're going to cover these formally today, but most of you just know from previous classes to find the mean of a set of numbers. You add up all the numbers, divide by how many there are. To find the median of the set of numbers, you put the numbers in order from smallest to largest, which they already are, and you find the one in the middle. And some of you probably even remember, if there's an even number of numbers here, then there won't be one in the middle. There'll be two in the middle. And so in that case, you add up those two in the middle and divide by 2. Or in other words, you take the mean of the two in the middle. So median, if there's an odd number of data points, pick the one right in the middle. If there's an even number of data points, you pick the 2 in the middle and add them and divide by 2 to find the median. And the mode is the one that occurs most often. So take a second and calculate these on your own just to get a little practice, and then come on back. Okay, so if you went through those, you probably came up with these numbers. And if you look at the numbers up here if we want to find one number that describes a typical value, well, 50 is probably not a good choice, right? Because 50 doesn't really describe a typical value. It's larger than all but one of the data points. So in this case, the mean is probably not a great choice. And you'll find out that's true. Generally, when money is involved, you don't want to use the mean, because the mean is affected by, in this case, by this number. Whenever you take the mean, it's going to be affected by extreme data values, which is why when the Bureau of Labor Statistics reports, or anybody really reports on income or housing costs, they always use when they talk about the average, they always use the median, because the mean would be influenced too much by extreme data values. So we need to make a note of that for the mean. We need to mention that the mean is affected by extreme data values, which is why it's so high right here. So there's certain cases where you just don't want to use the mean, because remember the goal here, we want one number to describe a typical value in our set of numbers. And if there's money involved, the mean a lot of times is not going to be a good choice. So the median and the mode, these are referred to as resistant measures. These are not influenced by extreme data values. So they are said to be resistant. And you can see that because think if I change this 150 into 900. If I change this 150 into 900, the mean is going to go way up, but the median and the mode will still stay at 30. Okay, so these two are said to be resistant. So let's say one of these employees gets a raise, which is a really good day, right? This person comes in, they were making 40,000. All of a sudden they get 70,000. That's a huge raise. So, yeah, that doesn't happen in retail. You don't get raises like that. At least you didn't used to. When I was in college, I had a retail job, and I can remember this part-time job. And I had been there, it must have been like 6 months or a year or some point where you get a raise. So my boss, brought me in the office, said, "Hey, Kurt, you've been here a while now. We're pretty happy with your performance, and we're going to give you a raise." And I remember thinking, "Oh, this is going to be great. I'm going to buy some new stuff." Actually, in college, I was basically just trying to pay bills. And it was something like, "We're going to give you an extra 7 cents an hour." And I remember thinking, "Oh my God, what am I going to do with all my new wealth?" So I don't know if it's still like that in retail. I hope things have improved, but I don't know. But this is definitely would be a nice raise, right? 40,000 to 70,000. So take a second. I have to do this. Don't just let me do the work. It's the only way you can get better. You have to try this. So take a second, press pause, and recalculate these. Okay, so hopefully you got these numbers. 5429, you can round this where you want to. It didn't say where to round, so you can round where you want to. Make sure you round correctly, though. Remember that we don't want to truncate the numbers. If you rounded the second decimal place, make sure you round correctly. But looking at what happened, you can see that, I use red just to emphasize, these stayed the same. But again, the mean is affected by every data value. So if there's a change, it will be reflected in the mean, because to find the mean, we add up all the data, right? So it's going to be affected by every single data value. So when a number changes, we would expect to see the mean change. So these stayed the same. They're called resistant measures. It's not that they can't change, but they don't change as quickly as the mean. So what we're going to do now is look at some symbols that you'll see in the book when it comes to the mean. I just want you to be aware of these symbols. I don't really do too much with them, but we should at least know what they're talking about. So looking a little closer at the mean, we pretty much know how to find the mean, but sometimes people refer to this as the arithmetic mean. So same thing, just another phrase you may hear. Somebody says the arithmetic mean, they're just talking about the mean. Add up all the data values, divide by how many there are. So here's the definition that most of you guys learned in previous classes. To find the mean, you add up all the data and divide the sum by the number of data values. So this phrase is reflected here and here in mathematical symbols. So as I've mentioned before, math is a universal language, so that even if people speak different languages, they can still read this correctly. So like when I was in grad school, I had an office mate from China, an office mate from Turkey, and we could struggle at times to communicate with each other, but with math we could communicate perfectly because everybody reads the symbols the same, regardless of your written language. So that's the strength of math. It just means that we need to understand some of the symbols. So this says this, and this, it also says this. So to see why, we need to look at this symbol here, this sigma. It's a Greek letter, capital sigma. And some of you know this already, but typically in math, well, just say math. In math, when you see this symbol, it usually means to add or sum, take the sum. And that's what it means here too. So like the alphabet that we use, there's capital letters and small letters. So capital sigma looks like this, small sigma looks like this. And we're going to use both of these because we use this for the standard deviation. So capital sigma, small sigma. And because my drawings aren't the greatest, that's, if you want to get a better drawing, you can look up sigma. But here's what it means. Here's what we need to know. So I'm just going to make up an example. So there's a sigma. I'll say I equals 1 to 3 of I squared. So when you see this, it means sum. We're going to add. And this is an index or a counter. And basically the way this works is it says start at 1. Do this to the 1, whatever this is. It could be really complicated, or in this case something kind of simple. And then go to 2 and put the 2 in here, and then finally go to 3. Stop at 3 because that goes up to 3. And you add these. So I start with the 1. I put the 1 right here. So what this is equal to is 1 squared. And then it's sigma, sum. So I automatically put a plus. So I have a plus. Now the counter goes to 2. It always goes in increases by 1, integer values. So then it goes to 2. So I put a 2 in here, and I put 2 squared. 2 squared. And then it's a sum, so I go plus. And then the counter goes to 3, and it stops at 3 because this basically says go from 1 to 3. So then we plug the 3 in here, it's 3 squared. And then we stop, right? If it said 1 to 5, we'd put a 4 squared, then a 5 squared. But it's just 1 to 3. Then we just do the math. So this says 1 squared, that's 1, plus 2 squared is 4, plus 3 squared is 9. And just a little review, if you have 3 squared, remember this means this is an exponent, or a power, however you want to say it. It says take 2 of these things, line them up and multiply them together, right? Take 2 of these 3's, line them up and multiply them together, and you get 9. Right, so that's something squared. So then come over here, we just add these up. 1 plus 4 plus 9 is 14. So we would say this is 14. So this is how this notation is used. We're really not going to do anything with it other than they use it in the book. So I just want you to, if you see this, it's not anything real tricky or scary. Once you see it, it just means sum. And a lot of times they will leave this part off, but it's understood this is going to basically say take the sum of all of our x values. What are our x values? Our x values are just the data values. So this is saying the mean x bar. Remember, x bar means mean, and more specifically mean of a sample. Where mu also means mean, but it means mean of a population. Both of them just say add up everything and divide by how many there are. So this is saying x bar, the sample mean, is the sum of all the data values, all these x's, divided by n. And n would be the sample size. So when you look at this, little n is always going to refer to the sample size, or in other words, the number of data values in the sample. So if little n is the sample size, what do you think big N is? Hopefully you're thinking the population size. It's population size, or in other words, the number of data values in the population. Okay, so when you think of the mean, you can just think of this. If you read it mathematically, it's written like this. And that's another strength of math, is the symbols are very concise. There's nothing extra and there's nothing wasted. So you can read this and it just takes less room to write than pretty much any written language will take. So that's it. X bar, add up all the values, add up all the x's. Each x is a data point. Divide by n, which is the number of data points, right? Same thing here. You have mu, which is population parameter sample statistic. So mu is coming from the population, right? You're taking the mean of the entire population as opposed to the mean of a sample that was taken from the population. So add up all the values, divide by how many there are. Okay, so that's the mean. There's really nothing new here other than this new notation that I just wanted you to be familiar with. But as far as the mean, we just add up all the data, divide by how many data values there are. Now what's probably going to be new to you is this trimmed mean. So let me make a little room here. So the trimmed mean says usually 5%. Sometimes it's 10%. But the trimmed mean, the advantage of this is it's more resistant than the mean. So if you remember the mean, the mean is not resistant because it adds up every single data value. And if there's an extreme data value, a giant one or a really small one, it's going to influence the mean. So the trimmed mean will oftentimes correct that because we're going to trim off values. So the trimmed mean is the mean of the set of data values remaining after trimming off the top 5% and bottom 5% of the data. When they say top 5%, they're talking about the largest 5%. And the bottom 5% are the smallest 5%. So, much like when you're calculating the median, we have to have the data lined up so we can trim off the top 5%, the top 5% of the largest numbers, and the bottom 5%, which is the bottom, the 5% of the smallest numbers. So, think about this. They call this the 5% trimmed mean, but we're taking 5% off the top and 5% off the bottom. So how much data are we really removing? It's going to be 10%, right? So we remove 10% of the data for the 5% trimmed mean because it means take 5% off the top and 5% off the bottom. Another trimmed mean that you see sometimes is a 10%, which means you take 10% off the top, 10% off the bottom, and this is 20%. But in our book, they always give us these 5% trim means. So if they ask you for a 5% trim mean, we're going to trim off 5%, the top 5% of the largest numbers and the bottom 5% of the smallest numbers. And then we take the mean of the remaining 90%. So we remove 10% of the data, we're left with 90%. And the key here is that if there are any large numbers or small numbers, we should trim them off, right? Because we're specifically trimming off the top 5% and the bottom 5%. So we take the mean of the remaining 90%. So we don't count those. We take the mean of the remaining 90%, and it just makes a trimmed mean that's more resistant. So to calculate the number of data values to remove, so when we're doing this, we always have to say, well, how many do we remove from the top and from the bottom? Numbers both top and from the bottom. So little n here would be the number of data values. And you just go through this little calculation here. So I'll do an easy one. Let's say we had 100 pieces of data and we want to find the 5% trimmed mean. Well, if we had 100 pieces of data, we'd go 0.05 times 100, which would give us 5. And then we'd take the 5 biggest numbers and the 5 smallest numbers and get rid of them. And just use regular rounding here, just normal rounding, just like you normally would. So if we got 2.6 here, we would round it to 3. If we got 2.1 here, we would round it to 2. So just use regular rounding. Okay, let's see what else we've got here. The median. So the median is the middle value in an ordered list. Okay, here's the key. Ordered list. All right, it's in an ordered list. I underlined it and wrote it in bold because that is the number one mistake. When students find the median, the number one mistake is to not put the numbers in order first. Just put them in order from smallest to largest. And of course, you could put from largest to smallest, but we're going to want smallest to largest because it plays into quartiles, which we'll be talking about later. So we want to, when finding the median, put the numbers in order from smallest to largest. There's a note here. This note says, I'm going to keep it in red because remember, red means danger. So we need red here. The numbers must be listed in what? In order. You might be saying, Kurt, you just said that. I know I just said that. I have to say that a lot because that's what you find out when you start teaching. There are certain mistakes that are just easy to make. So I nag a little bit extra in certain areas. This is one of those areas. So to find the median in order, make sure you put them in order. Okay. So then we've got a couple of cases here, which we talked a little bit about before. But for an odd number of data values, the median is the middle data value. So it's real easy. To find the median, if you've got an odd number of data values, it's just the one right in the middle. For an even number of data values, then the median is the sum of the middle two, right? So if you have 10 data values, there's not one in the middle, right? So you take the middle two, add them up and divide by 2, which really, if you look at this, we're basically taking the mean of the 2 in the middle, right? You take the sum of the middle 2 data values, divide by 2. Okay, so for the median, there's just 2 things that could happen. You could have an odd number of data values or an even number of data values. So with that, we've got a spot for you guys to practice. So let's do example, let's do both of these. Okay, press pause. Don't just wait. Don't wait for me to do it. You gotta press pause. Press pause. Trust me, that's how you learn these things. You have to do them on your own. So press pause, and let's have you guys try both of these. Keep in mind what we just talked about or nagged about the median. And then when you are done, press play. Okay, so to do the median here, first I have to put these in order, right? I have to put these things in order. So I'm going to go, all right, let's say 2, then there's a 3, and another 3, and a 4, and a 6, and then finally a 10. Okay, so they're in order. And now just looking, we have got 1, 2, 3, 4, 5, 6 values. So there's 2 in the middle, right? There's not 1 in the middle. So take a look at these 2 in the middle. The 2 in the middle are these 2. So I have to add those up and divide by 2. So you add those up, divide by 2, and you get a couple of possible answers. Some of you would have put 3.5, and some of you would have put 7/2. Both answers are fine. Usually I take a vote right now and say who put 3.5. And I say who put 7.2. Then I can tell something about the class, because some classes I found out hate fractions. Some students hate fractions. They would never write 7 over 2. They automatically put 3.5. So, I don't know because we're online, so I can't tell. I can't take a vote real quick. But I'm guessing we have some fraction haters in the room. Which are not in the room. I guess in your room. So hopefully not. Hopefully we will learn to love fractions just as much as we love decimals. But either of these answers are fine. However you want to do it, good with me. As long as you don't call this 7/2. Okay, that's not good. I have had that referred to as 7/2. 7/2 is the better way to say that. Okay, example 2. Let's try this one. Same thing. I'll put these in order first. We've got a 2. We'll put this one up here. Got a couple of 3s. We've got a 4 and a 6 and a 10 and a 15. So now we've got 1, 2, 3, 4, 5, 6, 7 pieces of data. So we're going to have one right in the middle. 4, right? So the median here is just 4. All right, so that's how you find the median. And the mode, this is the one that really is just not used that often. The only example I can ever think of, it's not a great example, but it's the only one I can even think of, is maybe if you have a clothing store. Let's say you have a clothing store and you've got maybe t-shirts that you sell. Just think of this example. You got t-shirts, and maybe you sell small, medium, large, extra large. Maybe you're gonna cut back on t-shirts, and you're just gonna sell the size that sells most often. So you'd be looking for the modal size. Okay, but really it's the value that occurs most frequently. It doesn't have very many applications. And there's a couple of notes, okay? So one note is that there may be no mode. There could be a value that doesn't occur most frequently, right? Maybe there's 7 numbers and they're all different, so there'd be no mode. The other note is this: some books, meaning some textbooks, not ours though, say that there may be more than one mode. Okay, so some say there may be more than one and others don't. And really an argument can be made for both. It just depends on how you interpret this definition. So I'll show you what I mean. Here's an example. So let's say we've got these numbers 3, 5, 3, 7, 2, 9, 7. Okay. Here are 2 ways you could answer it. Some people would say the mode equals, and they'd say, well, let's see, there's a couple of 3s, there's a couple of 7s, there's 2 modes. They'd say the mode is 3 and 7. Okay, so this is when I was originally taught mode, this is how I was taught. That there could be 2 of them, it's a tie. Okay, here's another answer. Here's how our author would say it. Our author would say there is no value that occurs most frequently because 3 and 7 both occur twice. So our book would say no mode. And I've looked at this on various software packages also. So I looked at Wolfram Alpha, Minitab, Maple, Excel, and in other textbooks. And it seems to be a 50-50 split. So for us, you can go with either definition that you want. Okay, when you look in the back of the book, and you won't be looking in the back a lot for mode because there's not that many questions about mode. But our book is going to do it like this. Our book is going to say there's no mode, but if you want to say the mode is 3 and 7, that's fine with me. They're both correct. It just depends on how you interpret that definition. And with a mode, because it's used so infrequently, it's really not even worth sweating over, to be honest. And I think that's why there's not a big push to standardize the way the mode is taught, because it's just not used enough. Okay, so either of these answers here are fine, but here's what's not fine. Here's what you can't do. Okay, don't do this. You can't just say the mode equals, well, let's see, 3 and 7. I like 7. You can't do that. That's not going to work. That's like making up your own definition. Okay, so that doesn't work. But either of these are fine. So here we have some data. And let's say these are weights of male students in Math 215. And what we want to do is find the mean, median, mode, and the trimmed mean. So we'll do this by hand first, and then I'm going to show you how we'll do it in reality in almost all cases. We're going to use the graphing calculator, but first let's just take a few minutes here. Don't worry about the trimmed mean yet. You can leave this one alone. We'll talk about that one, but let's have you guys just press pause a second and find mean, median, and mode, and see if we can come up with an agreement on those numbers. Remember, to do that, to find the median, we're going to put these in order. So go ahead and see what you come up with. So if we list them in order, we should get this here. To find the mean, we just add up all the numbers and divide by how many there are. And there's 15 data points. And so to find the median, we find the one in the middle. So we got 1, 2, 3, 4, 5, 6, 7. And then if I count 7 from the other side, I'll be right here because there's 15. So this 162 is right in the middle. So that's the median. And then the mode, 155 shows up twice. So remember, for the mode, let's say there were a couple of 180s also, so there's a tie. Then you could say no mode, or you could list them both. Totally up to you. So to find the trimmed mean, so this is the one that you're probably least familiar with. So what we have to do to find the trimmed mean is we want to find, it's 5% trimmed mean, so we need to calculate first. So let's do this. Let's go 0.05 times n, which in our case is 15. So if you run through the math there, you're going to get 0.75. And we do regular rounding, right? We just round to 1. Just think, is 0.75 closer to 0 or closer to 1? Closer to 1, right? So that means the way we find the trimmed mean is we are going to take 1 off the top and 1 off the bottom. Meaning, if these are in order, here's the 1 off the top, here's the 1 off the bottom. So we basically get rid of these two and then take the mean of these remaining. So in this case, we don't really have any extreme values, so it won't change much, but there have been a couple of times in the past when I do this in the classroom, I pass this sheet of paper around and have students write their names, and every once in a while I get kind of a smart-ass student who will put something like, there'll be an outlier of like 670, and like 670, somebody in here carries their weight extremely well, or that's the wrong answer. But it actually works out well because it's an example of an outlier, right? So 670, if you put that in here, this mean is gigantic. And then with the trimmed mean, it gets back to normal because it trims it off. So for this particular year, when I got these numbers, everybody was, nobody put down any crazy number like 670. So anyway, in this case, what we would do, we're going to trim off 1 off the top and 1 off the bottom, and we're going to recalculate the average of these that remain, right? So it's just the mean, but it is the mean of these remaining values. We'll try a new color here. So we're going to do the mean of these remaining, right? We're not going to consider the last two. So if we recalculate the mean with the 13 remaining numbers, then we'll get our answer. So our trimmed mean is equal to 167.4 if you round to the nearest tenth. Again, you can round where you want to, just round correctly. So the trimmed mean, it went down a little. The trim mean didn't do much in this case because neither of these were outliers, so it didn't make a big difference. It was 168.4, now it's 167.4, so not a whole lot of change here. Had there been a large outlier, though, there would have been a big change. So we know how to do these things by hand. It's very tedious by hand, and in reality, nobody really does these by hand anymore. So we're going to learn how to do this on the graphing calculator. So I'm going to show it, of course, on the TI 8384. There's a couple variations of the software, depending, if you have a TI 84, depending on how new it is, there's different variations, but they're very similar. So we're going to use this list command, one variable stats, and sort. So this is what we're going to learn about. And then we'll do the same thing we just did, but we'll do it in the calculator, which is much easier. But here is one thing you really have to be careful about. When inputting data in your calculator, always double check. You have to double check. So attention to detail is super important in math or any of the STEM fields, right? STEM, science, technology, engineering, mathematics. We have to keep that in mind. Attention to detail is super important. So don't just put the data in your calculator and assume everything's right. It's too easy for mistakes to be made. So always double check. And what happens every time when I'm, in the classroom, I'll have a quiz or a test, and it's really easy points because I'll put like 20 numbers and I'll just say, put it in your calculator. What's the mean, the median, and we talk about standard deviations, and all these things are calculated instantly on the calculator, and you just have to list the answers. But sometimes what will happen is, there'll be 6 or 7 answers to be listed there, and every one of them is wrong. And almost always it's because somebody didn't double check. If you have bad data, you're going to get wrong answers every time. So it's really important to make sure you double check when you do this. So I've got a video of how to use the calculator. So let's take a few minutes and take a look at this one. Okay, so to use the calculator, we need to put the data into a list. So the way we do that is you go to the stat button right here. Just press that stat button. And then you come up with this screen and you want to go right to edit. So then hit enter. So this one, I've got a couple lists in here with numbers in there. So the easiest way to get rid of those is to go up to the name of the list. See how L2 is highlighted? And then you press the clear button. And then you can hit either down arrow or enter, whichever. It will clear it out. You can also go in here and delete each number. That works too if I just hit delete. One thing that happens sometimes is students will go up here and hit delete. And then it looks like the list is gone forever. And you're like, oh my God, I need to buy a new calculator. Well, you don't. To get that back, if that ever happens, if you ever accidentally delete a list, just go to Stat, and then go down to number 5, Setup Editor. Just hit Enter, and it says done. Then when you go back to Stat again, Edit, it's back. So what I want to do is get rid of those values, so I'm just going to go up to list 1, and I'm not going to hit delete, I'm going to hit clear. And then either down arrow or enter. Either one works. So that clears them out. So what we need to do is put those numbers into the list. And we just go through and type them in. Hit 195 and then hit enter. And you just go right down and put them all in the list. And don't worry about putting them in order. I'll show you how to sort them. We just want to have all the numbers in here. Okay, so once numbers are in there, then we can go to stat again, the stat button. Whenever you're not sure, just think, what's my favorite class ever in the whole world? Oh yeah, statistics, right? Press stat, and then this time we want to go over to calculate. So you hit the right arrow, calculate. And this command here, one variable statistics, we're going to use all the time. It will basically just give us basic statistics for a set of numbers in a list. So we're going to use that one all the time. So you go one variable stats, so you hit enter. And now here's where it kind of depends on your software. Sometimes you'll come up with this, depending on what software you have. And it's really just saying the list. It's saying, where is the list? List 1. Okay, so you want to say list 1 because that's where we put it. By default, it will. Frequency list, you want to leave blank, then go to calculate. Now, some other versions are just going to say one variable stats, and that's it. But once we hit enter, we should all have the same thing. And you can see the mean there was calculated as 168.4, which is what we got. And notice that this N has an arrow. So an arrow pointing down. So if I hit this arrow pointing down right away, there's more information here. So just to see what we've got here. Okay, we've got the mean, X bar. We've got some other things we don't need. There's standard deviation, which we'll talk about later. It says N equals 15. Remember, that's the sample size, 15. You've got the minimum value. We've got quartiles, the first quartile, which we'll talk about later. We've got the median though, right? The median 162, which is what we calculated by hand. Third quartile, again, we'll talk about that later. And then maximum. So if we wanted to put these in order, which we won't really have to do very often at all, but if you did want to put them in order, here's how you do it. So in other words, when we look at our list, so let me go back, so stat, edit, there's our list, the same order we put them in. If we want to order that list, we can go to stat, and then see we've got sort ascending. That's what we want. We want to sort them in ascending order, so from small to large. We have to tell the calculator which list. So we want to tell list 1. So see above the number 1 it says L1. So to get to that we need the second key. That's this blue key here, second L1, and then hit enter. And it just says done. It doesn't look like it did anything, but it did, because if you go back to stat and go to edit, now they're all in order. And that makes it easy to find the 5% trimmed mean, because we calculated by hand that we have to get rid of the largest number and the smallest number. So the smallest number is right here, 125. So to get rid of that, just hit the delete key. You hit this delete key right here. That's gone. Then I have to scroll down to the bottom to get to the biggest number, which is 225. Then hit delete. Okay, so those two are gone. So now we have 13 data values, and we just have to recalculate the mean. So all we do is hit stat. We want one variable stats, right? Because that will give us the mean. Go over to calculate, and then just rerun the one variable stats program. It's going to just rerun the program, but with only 13 data points this time. So go down, and all we care about is the first number there, the new mean, which is 167.4 with rounding, which is the same thing we got before. So make sure you're comfortable inputting numbers into the calculator and running the one variable stats. Trimmed mean you'll see sometimes, but we will all the time had to put numbers in a list and run the one variable stats. So make sure that you are comfortable with that one, and let me know if you have any questions. Okay, so hopefully you're all set with the calculator. It takes a little practice, but there are tons of YouTube videos for anything you want to do on a TI-8384 or any calculator. You can just watch a few YouTube videos and you should be able to figure it out without too many problems. So another type of average we need to look at is what's called the weighted average. And you may have experienced these in your classes, because sometimes you'll have a class where the final exam is counted twice. That'd be like a weighted average. So whatever you get on the final, it's kind of like you got two of those tests. So it's weighted twice as much as a regular test. So sometimes you want to average a set of numbers, but we want to assign more importance or weight to some of the numbers. So the one that we'll take a look at is page 101, number 24. And it says find the weighted average of a set where, and it says, I'm just going to kind of sketch this out a little bit. It says that 10 has a weight of 5. 20 has a weight of 3. So this way I'm writing is not any formal way of writing it. I'm just kind of taking notes. 30 has a weight of 2. So this shows the importance. Weight is just a way of showing importance. Like whatever this 10 is, it's pretty important because it gets weighted 5 times, right? Wherever this 30 is, it's not as important because it gets weighted twice. So just to see, what if we just took the mean of these numbers? Let's say, forget about the weights, just take the mean of these numbers. So if we wanted to just find the mean, and they're not asking us to, I just want to show this just so we can compare. So if I took the mean, I'd say, well, it's 10 plus 20 plus 30, right? Add up the numbers and divide by how many there are. There's 30 of them. So that gives us 60 over 3, which gives us just a mean of 20. So here's what we should expect. With a mean of 20, well, this 10, if we take the weighted mean, 10 is weighted a lot more. So there's going to be more weight on the 10. Since the 10 is below this mean, probably the weighted mean is going to be less than 20. Because here when we took the mean, all numbers counted the same. There's a 10, a 20, and a 30. They're all treated equally. You add them up, divide by 3, and you get 20. But if we assign more importance to this 10, right, as opposed to these have less importance, because this has a weight of 5, this only has 3 and this has 2. So if this has more weight, it would tend to make this smaller, make it more like the 10. Okay, so that's basically what we would expect. So let's see how I'd find the weighted average. So they say find the weighted average. So we could do this. We have the weighted average. We don't really have a symbol for that. We just call it weighted average. But what we're going to do now is we're going to do it this way. We're going to say, okay, we're going to count that 10, but it's going to count 5 times. And then we're going to count the 20, and it's going to count 3 times. And then we're going to count the 30 twice. So we're going to add those up, divide by. And here's the part that sometimes we get bogged down in. We can't divide by 3 here. So to see what's happening, think if we did it like this. If we have that 10, but it counts 5 times, it's sort of like doing this, right? You don't normally write it like this, but just to see what it really means, weighted. If the 10 is weighted 5 times, it's sort of like we had 5 of those 10s. Then the 20 is weighted 3 times, so we're adding 3 of those. And then the 30 gets weighted twice, so we're adding 2 of those. So if you're going to take the mean of all of these numbers, what would you divide by? And if you look, there's 10 data points, so we divide by 10. So that's what we do here. When you find the weighted average, you divide by the sum of the weights. So 5 plus 3 plus 2 is 10. So we can't divide by 3 because there's 3 different numbers. We divide by 10 the sum of all the weights. So then if we do this, we're going to get 50 plus 60 plus 60 over 10. Right, I'm just doing the math here. 10 times 5, 20 times 3, 30 times 2. And that is going to give us 170 over 10, or a weighted average of 17. So the weighted average is 17, and like we had talked about, because the 10 is weighted more, it'll pull this mean down, which you did. So to find the weighted average, you just do this. You have to figure out how the numbers are weighted. We still have to tell you, and then you just incorporate that in and add all these up in the numerator, divide by the sum of the weights. So there'll be a couple of them in there in the homework for you to work on in the book. And then we've got the last topic in this section is distribution shapes and averages, because the average will be affected by these shapes. And these are three that we've seen before, but we didn't really talk a lot about them. So we're going to take a closer look today. So if you have a histogram like this one, which is mound shaped, it's mound shaped, it's symmetric, so it looks, like you could split it down the middle, and it's the same on both sides. So if you have one like this, well, you can see, so remember this is a histogram, here's the number line, it's a number line. Well, the mode number is right here, right? This one occurs the most. So if you have a distribution shaped like this, here's the mode, the one that occurs the most. And when it's symmetric like this, it'll be the case where you've got this number right here, that's the mode, but also the mean and the median will be the same also. So you got the mean, got the median, you got the mode. Now if this were perfectly symmetric, they'd all be equal. In reality, they're usually not perfect, so we'll say they're close. So when you have a mound-shaped or symmetric set of data, the mean, median, and mode, we could say all are equal or close. Okay, so here's the mode, the tallest one, and the mean and median will be pretty much the same. Now what could happen is if, let's say you have something skewed right, which means the tail is on the right. So just imagine if there were all of a sudden some numbers way over here. Think if these numbers are way over here, very extreme on the number line, way out here. Which one of these will be affected most by extreme data out here? It's going to be the mean, right? The mean, whatever the mean is going to be pulled in that direction. So that's what we'll look at next. Actually, I should mention one other thing before we even do that. If you think of this geometrically, the median for any graph, the median cuts the area of the graph in half. This isn't something you need to know, but it'll make it a little more interesting maybe and easier to see. So for any distribution, the median cuts the area in half. What you can see right here, the area on this half is the same as this half. And the mean will find the balance point. So for the mean, think of if you were to cut out a shape just like this and you're trying to balance on your finger here, the mean is the balance point. So for this one that's perfectly symmetrical, of course the balance point's right there in the middle. So it's just another way to think geometrically of these shapes. So if you have a distribution that is skewed right, and I'll tell you, sometimes what you'll hear that referred to is positive skew. So positive skew is the same as skewed right. You can kind of think of it like this. If you have a number line, here's 0. To the right of 0 are the positive numbers. To the left of 0 are the negative numbers. So you can associate skewed right with positive skew. Our book calls it skewed right, but probably just as many times it'll be referred to as positive skew in other areas outside of our book. So when you have one like this, you can see right here, here's the mode. The mode's right here. Right, that's the tallest number, that's the mode number. So like we talked about before, these values way out here are going to pull the mean in this direction. So if this were symmetrical at one time and then you have all these values out here, this value way out here is going to pull the mean in that direction. So the mean, as you know, is influenced the most by those kind of values. So you could say, I mean, I'm just sort of guessing, but the mean will be pulled to the right with that number. And then the median will typically be in between these two somewhere. So in between here somewhere is the median. Now we will calculate all these with a calculator, but just to get an understanding of how these interact as these get pulled to the right. Data like this comes from being bounded below, usually by 0. So here are some examples of distributions that are skewed right. People's incomes, right? Because you have a 0 as a minimum. And then think of an income. So if there's a, if this is a number line, there's very few people way out here, right? Really wealthy, there's just a few people. The bulk of everyone is down here in this area. So people's income have a right skew, housing prices. Again, this is why we don't usually use the mean when describing these, because it gets pulled by these. Number of kids in a family. This would have a right skew, and maybe a scores on a difficult test. Think if you take a difficult test, there's going to be a few people over here that get like 95%. On a difficult test, the bulk of all the scores are over here in this area. Right? There's a whole bunch. Remember, so typically this vertical axis will be quantity, right, or frequency. So the taller the bar, the more numbers there are there. So if this is a score of a test, there's very few of them way over here, like at 90, 95, 98, things like that. There's a whole bunch of them way down here. Maybe this is 30%, 40%. So that's just an example of skewed right, and we can see that the mean will be pulled to the right. So for skewed left, that one, of course, also can be referred to as negative skew. So this one would look like this. We can see again the mode value right here. This is the one with the highest frequency. And then, of course, these values way out here are going to pull the mean with them in this direction. So the mean is going to be over to the left. You could think of it again as the balance point if you were trying to balance this object. So the mean would be somewhere over here. And then the median, geometrically, it's where it would cut the area in half, but it's going to be somewhere in between these. And there are not as many examples, real-life examples of distributions like this, but it comes from being bounded above. So probably an easy example to see would be an easy test. An easy test. If you take an easy test, there's going to be few students down here. Remember, this is a number line, right? To the right, the numbers grow. So numbers to the right are bigger. So there's very few students who didn't do that well, but over here, as the numbers get bigger, there's more. The frequency is more. So that's an example of a negative skew or skewed left, and the mean just gets pulled to the left. Just like in this case, skewed right, the mean gets pulled to the right. So that's pretty much it for 3.1. So you guys know what to do, right? We have to work a little extra for this online. So make sure you make yourself do the homework. And if you have any questions, make a little note of it and get a hold of me, right? Email or stop by for office hours and let me know what you're having any trouble with.